In this video, we're going to look at a topic known as limiting reactants. In the stoichiometry problems you've dealt with so far, you've only been given the amount of one of your reactants, one of your starting reactants. You've just assumed you've had an unlimited amount of the other reactant. However, that's not a very realistic situation, where in real life, you know the amounts of both of your starting reactants. Odds are as well you don't have exactly the correct ratio of those starting reactants, and one of them will actually run out first. A good example of that is in this picture here, where you have a huge number of red balls, but just one blue ball. As that reaction proceeds, you combine a red and a blue ball to make your product, but after just one iteration of the reaction, you're out of blue balls, and the reaction stops. That is to say, the reaction is limited by that single blue ball. Another example of this situation. You have some red starting reactant and some green starting reactant. The reaction proceeds, you make some blue product and some purple product, and it proceeds and proceeds and proceeds, and you make more product and use up more reactant until eventually you're entirely out of green reactant. At that point, it's entirely possible you still have some red reactant left over. You have some excess of that red. So we can go ahead and label these things. We can call that green reactant the limiting reagent, or what ran out. The reactant that limits the reaction. And we can call that red reagent or red reactant the excess reactant, what there is excess of. It's that green reactant, that limiting reactant, that we're really concerned with in these problems. Here's one more way to visualize it. Let's say you had 8 car bodies and 48 tires. Each car requires 4 tires, meaning you can combine the 8 bodies with 32 car tires to make 8 cars. At that point, you'd have 16 tires left over. The reaction would stop. The assembly of cars would stop as you ran out of car bodies. Likewise, in this reaction here of hydrogen and nitrogen to make ammonia, you might have a beaker full of hydrogen and nitrogen molecules. They'll combine together and they'll assemble a certain number of ammonias, but at that point you'll have a couple of nitrogens left over. Here, hydrogen was our limiting reactant. When it ran out, our reaction stopped, and nitrogen our excess reactant, what there was some left over of afterwards. Let's look at that reaction in a bit more detail. It's called the Haber process, and it's really used to manufacture ammonia, an important ingredient in fertilizer. Here's Fritz Haber, the German chemist who first came up with the industrial synthesis of ammonia. We want to balance our equation, putting a 3 there and a 2 there. And in the background, I apologize for the graphics, but I was trying to show some pictures of nitrogen, hydrogen, and ammonia. So the question reads, predict the following. How many moles of ammonia will be produced from the complete reaction of 10 moles of nitrogen and 10 moles of hydrogen? What I want to do is set up 2 different reactions, or 2 different equations, and figure out how much product 10 moles of nitrogen would be able to make, and how much product 10 moles of hydrogen would be able to make. I'm going to consider them individually, and then see which one produces less, as that will be my limiting reactant. So my 10 moles of nitrogen will form 2 moles of ammonia for every 1 mole of nitrogen. That's my mole-to-mole ratio. Likewise, my 10 moles of hydrogen will produce 2 moles of ammonia for every 3 moles of hydrogen. That nitrogen, if all of it reacted, would go on to make 20 moles of ammonia. The hydrogen, on the other hand, is only capable of making 6.67 moles of hydrogen. That is to say, after making 6.67, that should read 6.67 moles of ammonia of product. That is to say, after making 6.67 moles of ammonia, I will be out of hydrogen. I would still have some nitrogen left over, because that nitrogen could go on to make 20 moles of ammonia, but it won't, because that hydrogen will be gone. It will be used up. So in this case, nitrogen is my excess reactant, hydrogen, my limiting reactant. Here's that same equation. Predict the following. How many grams of ammonia will be produced from the complete reaction of 20 grams of nitrogen and 10 grams of hydrogen? And again, a real-life situation where you're given the starting amounts of both of your reactants. So I'll start with what I'm given in both cases. 20 grams of nitrogen and 10 grams of hydrogen. I first want to convert to moles by multiplying by the molar mass. Then use a mole-to-mole ratio. 2 moles of ammonia get made for every 1 mole of nitrogen consumed. And the same thing with hydrogen. Each mole of hydrogen has a mass of 2.02 grams. And I produce 2 moles of ammonia for every 3 moles of hydrogen. In this case, when I do the math through, I find that I have enough nitrogen to produce 1.43 moles of ammonia and enough hydrogen to produce 3.33 moles of ammonia. Just like before, I won't actually produce those 3.33 moles. I don't have enough nitrogen. The nitrogen will run out after making only 1.43 moles of ammonia. So let's take that 1.43 moles and convert it to grams. That gives me 24.31 grams, or because I have 3 sig figs, 24.3 grams. Again, 20 grams of nitrogen could make 1.43 moles of ammonia. My 10 grams of hydrogen could make 3.33 moles, but it won't because I'll run out of nitrogen. Now at that point, there'll be some hydrogen left over, and we could go back and solve for it, but we'll save that for another day. To switch equations here, identify the limiting reactant and the theoretical yield, that is to say how much should form, of phosphorus acid, H3PO3, if 225 grams of PCl3 is mixed with 123 grams of H2O. Just like before, let's set up 2 different reactions. 125 grams of PCl3, I want to convert that to moles, use a mole-to-mole ratio, and figure out how much phosphorus acid it could produce. 125 grams times the molar mass times the mole-to-mole ratio, 1 mole H3PO3 for every 1 mole of PCl3 used. That'll tell me moles of H3PO3 that form. And with water, each mole of water weighs 18.02 grams. And I'm producing 1 mole of H3PO3, and it's costing me 3 moles of water every time I do that. When I go through and solve these, I find that I have enough PCl3 to produce 1.638 moles of phosphorus acid, and I have enough water to produce 2.27 moles of H3PO3. However, I will not produce those 2.27 moles because my PCl3 will run out first. That is to say, water is my excess reactant, PCl3 my limiting reactant. After producing 1.638 moles of H3PO3, I'll be entirely out of PCl3 and I'll have some amount of water left over. Again, we could go back and we could solve the amount of water left over. We'll save that for another time. To finish up the problem, let's take the 1.638 moles of H3PO3 produced, multiply by the molar mass of H3PO3. And we find that we produce 134.32 grams of H3PO3, which if we converted to 3 sig figs, 134 grams of H3PO3. Two more slides. The theoretical yield, as I alluded to earlier, is the amount of product that should form when you do the math. Should form when you do the math. The actual yield is the amount that actually forms. That's to say that in real life, things don't go according to plan all the time. According to plan. Sometimes you produce products you didn't intend to. Sometimes reactions don't proceed as far as you'd like them to. For a variety of reasons, sometimes things happen that you don't intend, and your actual yield is less than what theoretically could have come out of that reaction. Finally, your percent yield is just dividing the actual yield by the predicted yield, or the theoretical yield, and multiplying by 100. You see in this particular reaction there was a percent yield of 83%, or if we were to plug in some other numbers, for instance, maybe your actual yield in some reaction was 100 grams, when in theory you were hoping to get 134 grams. You notice that those numbers are taken from here, where the reaction predicted 134 grams, but maybe for some reason you only produced 100 grams. Could multiply that by 100, and we would find that the percent yield of this reaction is 75%. That you only produce 75% of what you should have, and your other reactants made some other sort of product or didn't react. But it turns out 75% is actually pretty good, and I think an industrial chemist would be pleased with that percentage. So we'll look at one final problem that involves the Haber process. Determine the limiting and excess reactants, the theoretical yield, and the percent yield if 14 grams of nitrogen and 9 grams of hydrogen react and 16.1 grams of ammonia form. Just like before, I want to set up two different reactions and go through and see which one of these is limiting. So I have 14 grams of nitrogen and 9 grams of hydrogen. I'm going to convert these to moles by using the molar mass. Each mole of nitrogen weighs 28.02 grams. Use a mole-to-mole ratio and say that 2 moles of ammonia form for every 1 mole of nitrogen. That'll tell me the moles of ammonia that would form if all 14 grams of nitrogen react. And then with hydrogen, I want to say that each mole of hydrogen weighs 2.02 grams. And that again, I produce 2 moles of ammonia for every 3 moles of hydrogen that react. Doing this math through, I find that I would produce 1 mole of ammonia, but I have enough hydrogen to produce 3 moles of ammonia. Will that 3 moles of ammonia form? No, it won't, because there's not enough nitrogen. To label some things again, nitrogen is going to run out after producing 1 mole of ammonia, so it's my limiting reactant. Hydrogen could go on to produce 3 moles of ammonia if there were more nitrogen. It's my excess reactant. So let's take that 1 mole of ammonia that forms, because there's enough nitrogen and enough hydrogen to make 1 mole of ammonia, multiply it by 17 grams per 1 mole, and find that I produce 17 grams of ammonia when 14 grams of nitrogen react with 9 grams of hydrogen. Now the last part of the problem says that in actuality only 16.1 grams of ammonia form. That's my actual yield. The math said 17 grams of ammonia should have formed. Multiply that by 100. We find the percent yield for this Haber process reaction is 95%. Pretty good.